Let's talk about the subject of solenoids and toroids. A solenoid is a device that's got a certain number of turns per unit length, and that's it. That's the definition of the solenoid. What I've done here is wrapped it around a metal nail. Well, this accomplishes two things. One is it's easy to make a solenoid this way because you have something to wrap it around. And secondly, the iron, it turns out, increases the magnetic field effect by about 5,000 times. So that's like putting a dielectric in a capacitor. Just like you put a dielectric in a capacitor to increase the amount of stored electrical energy, putting a metallic object inside a solenoid increases or focuses all its magnetic energy by a big factor. Here the factor is 5,000. So ordinarily, if I just pass two double 1.5 volt batteries into this wire, it's not going to do much of a magnetic field, but because of this 5,000 fold increase, you can see that it will lift some objects. Well, naturally there's no lifting effect right now, but let's try to pass the current. So the slight caution I have to exercise here is that I should not hold this for too long or my hand will burn, fingers will burn, because the current is really high, because the resistance is really low. You can see that it lifts it easily, and if I release the wire, the object is also released. Powerful electromagnets are found in junkyards to lift crushed automobiles, and in other areas of life, such as even your doorbell has got an electromagnetic relay. What happens there is that when you press the doorbell, current flows through this something that looks like this, and then it moves back and forth many times because of the fact that the current flowing is an alternating current. So here I have a toroidal coil. What this is you wrap a wire around something that looks like a donut or a bagel. Here I have a giant O-ring I picked up from somewhere. So you have an interesting feature. A certain number of turns. Outer turns are more widely spaced than the inner turns, obviously. And both the solenoid and the toroid have an interesting feature, and that is the magnetic field is almost entirely focused inside those objects. So a solenoid's magnetic field is contained inside the solenoid. There's very little coming out, and anything that comes out is in the nature of a defect. So in the capacitor you'll have these little edge effects. Similarly here also you'll have some things poking out like that at this point and this point. The toroidal case is even more precise. There is no edge effect or anything, because in a sense the two edges of the solenoid are identified and you make a torus out of that. So this just, the flux lines keep flowing through and there's no edge effect or leakage in this case. So it's a very efficient design for high quality transformers, and any good amplifier should have a toroidal transformer in it. Let's look at the derivation of the magnetic field of a solenoid and a toroid. Solenoid, the groundwork has already been laid a little bit, because in the previous video I talked about ribbon cables. Let me just remind you of what that is. You have n wires per meter carrying current in a certain direction. Let's say it's outside, and then you do an Amperean loop. And if you've not done this, please go and look at the previous video. You'll find that the magnetic field of the ribbon cable is just mu naught times n times the current in each wire. So I is the current in each wire. Now if I have, instead of one ribbon cable, two ribbon cables, put one below the other, what will happen? So you can see that this is starting to look more and more like our solenoid situation, except that I'm taking a cross section of the solenoid lengthwise and looking at the currents coming out like this and going in like this. Okay, so what's happening here vector wise? Mu naught Ni, by using the right hand rule for Biot-Savart law, when the current comes out of the page, the magnetic field follows the direction of your fingers. So the magnetic field from the solenoid is going to be down like this and up like that. And because the magnetic field does not depend on the z coordinate, it's going to look like this throughout space. and I've just drawn it in one location. It's the same everywhere. Then let's now look at the magnetic field produced by the lower parts. By the same Biot-Savart law, thumb rule is going into the page, so magnetic field is going to be to the right above and to the left below. Right above, left below. You'll observe almost exactly like in the capacitor case. In the capacitor also you had the same situation. You had the positive plate of the capacitor, the negative plate of the capacitor, electric field doubling in the middle and electric field cancelling out. The solenoid is exactly the same in spirit. The magnetic fields cancel outside the solenoid, which is why I have the statement that outside the solenoid the magnetic field is close to zero. And inside the solenoid, the magnetic field actually doubles. So B sol, that's actually mu naught Ni over 2. So B sol is mu naught Ni, because 2 times mu naught Ni over 2 is mu naught Ni. For the ribbon cable, it was mu naught Ni over 2 in the previous video. So that's video 9C. So that's the formula for the magnetic field of a solenoid. The magnetic field is not very big. If you think about it, mu naught is 4 pi times 10 to the minus 7 Tesla meter per ampere. And if you look at the number of turns here, I'm just guesstimating, that's 10, 20, 30, 40, 50. So the number of turns per foot is about 50, so per meter is about 150. Even if you make it as high as 200, little n will be 200 TPM, or turns per meter. And the current is going to be something like an ampere, let's say, through that solenoid. So I'll be getting something like a pretty small magnetic field. B sol will be 4 pi times 10 to the minus 7. 4 pi is around 12. So the 12 times 10 to the minus 7 times 2 times 10 squared. So that's 24 times 10 to the minus 5 Tesla. Pretty small. It's about 2.4, well, 240 microteslas if you think about it. It's about 4 times the Earth's magnetic field. It's big enough, but not enough to cause serious ripples in the magnetic field profile of even the Earth. So if you do add the nail, so like I'll call that B nail sol, well then everything's going to be multiplied by the factor known as kappa, capital kappa, not to be confused with lowercase kappa, which is what is used for the dielectric constant of a capacitor. Here this is called, this has got no fancy name, it's just called relative permeability. Some textbooks maddeningly call this mu sub r, and I hate that, because then you'll have a formula that looks like mu sub r mu naught little ni, and the textbooks do the same thing for the little kappa. They call it epsilon sub r, and then your capacitor formula looks like epsilon sub r epsilon naught. It's just pretty awful notation in the old textbooks, but very popular, I must say. So if you see mu sub r, just replace it mentally with capital kappa. Capital kappa unfortunately looks like capital K. The Greek letters and the Latin letters coincide for a lot of the alphabets. So here I do have 5,000-fold increase. So that's going to be 24 times 5 times 10 to the 3. So that becomes 10 to the minus 2 Teslas. And that's pretty big. 24 times 5 is 240 over 2. So that's going to be 120 times 10 to the minus 2 Tesla. Well, that tells me it's 1.2 Tesla. Probably not true in my simple electromagnet. So maybe in my case the current was more like 0.1 amperes, because I don't think it was more than a tenth of a Tesla there. It was able to lift a paper clip, but I bet it could not lift anything serious. So that's so much for a solenoid, and in one of the homework problems you'll be asked to build a solenoid to certain specifications. So just to summarize, the solenoid's magnetic field is everywhere parallel inside the solenoid. Outside the solenoid it's zero on either side. Now how do two ribbon cables become a solenoid all of a sudden? Well, what I'm doing is cheating. I'm taking a ribbon cable on the top, ribbon cable below, and imagining they meet at infinity and infinity over here. Well, what's really happening is infinity is about a centimeter. But turns out not a bad approximation at all. Now let's look at toroids. What I'm going to do is I'm going to take this bagel and cut it with a bagel slicer. Then what I'm going to get is a figure that looks like this. That's the bagel itself. And let's put some radii on it. Our usual custom has to be to give an inner radius of A and an outer radius of B. Let's stick with that custom. And then we are going to have some currents coming in, and here I have to be careful not to undercount or overcount. So what I'll do is I'll put a current anti-current pair immediately so that I don't make that mistake. Now in a real solenoid, when you try to make a toroid, in real time, you will find that there's probably one more or one less of these things by the way that winding works. But because the number of turns is close to 1,000 in real applications, that little extra asymmetry will not affect things that much. So I'll just stop at 8. Okay, so now here we have n actual turns. Capital N is always used for the total number of turns, and little n is used for the number of turns per length. Okay, so now we have to look at Amperian loops. The obvious Amperian loops to choose are going to be circular in nature, concentric with the center of the torus or the donut. So 1 Amperian loop, 2nd Amperian loop in the middle between A and B. That's where you may expect most of the action to happen. And the 3rd Amperian loop is outside. You can quite immediately see why the magnetic field outside and inside the hole of the donut, and outside the donut is going to be exactly 0, because inside, current enclosed 1 is 0, because there is no current enclosed inside C1. Let's take the directions to be counterclockwise, just like that. And what about current enclosed by C2? Yes, it does have current. The current enclosed by C2 is 8 times I. Let's say I is a current in each one of them. So yeah, or in general, it's n times I. So let's just do that. I enclosed 2 is going to be n times I. And then I enclosed 3. Well, what happens there is you have a positive Ni, and that's evenly balanced by a negative Ni from those. So that's 0 outside also. And that's the reason why there's no magnetic field, because Ampere's law, if you recall, is a statement that the circulation of the magnetic field along any of these Amperian loops Ci, where I goes from 1 to 3, is equal to mu naught times the current enclosed by the ith loop. So the left hand side of Ampere's law for this sort of symmetry will work the usual way. So let me just run through that a little quickly. Now I expect from Biot-Savart law that the magnetic field of, let's do it for C2. I expect that the magnetic field for each of these wires is going to come out like that. Okay, they're going to be in concentric circles. So I can expect the magnetic field, the tangential component thereof, to look like this. The ds vector, the arc length vector, is always going to be tangent to a circle. So bt and ds are going to be parallel throughout C2. For C1, there's nothing to do since there is going to be no magnetic field there, and there's going to be no magnetic field here. So I'll focus on C2. So the left-hand side of Ampere's law for C2 becomes BDS cosine 0 degrees Now the magnetic field will only depend on the floating radius r of the Amperian loop. So I'll get B of r integral ds C2, and that of course is the circumference of a circle, a well-known result that does not need to be derived. But those who want to do it can also do it using calculus. Once I have that, I can set it equal to ni, and mu naught times ni. So I have B of r times 2 pi r equals mu naught capital Ni, and that tells us that magnetic field as a function of r is mu naught Ni over 2 pi r. Now it obviously seems to depend on r. So if you plot this magnetic field profile, it looks like this. So between 0 and a there's nothing. Between b and infinity there's nothing. Between a and b it's going to go as 1 over r. But one of the cool properties of 1 over r function, it doesn't change much when you're far away from the origin. So this actually is considered to be quite linear, even though it really is not. For most industry purposes, it's considered actually quite linear. And that's one of the great applications of a toroidal coil. Once again, for the purposes of construction and enhancing the magnetic field inside or the flux inside, the toroid is not made of rubber, like in this case. This is a demonstration toroid. In a real toroid, you'll have laminated iron core, like in transformers, for example.